So last time we actually got to do some calculus in our Calc 3 class, and now we're going to make good on the 3 part of Calc 3 and move ourselves into 3 dimensions. Section 10.1 is called Introduction to R3, and you'll notice the R looks a little funky. It's got a double bar there. That symbol is what we use in math to refer to the real numbers. Okay, and that's like what you would think of as the real number line. Okay, so it's a one-dimensional line. If we say R2, that means we've got two real number lines put together. That's your XY plane. R3 is where we move into the third dimension. All right, so let's hop over to GeoGebra to learn about R3. What you're looking at here is R2, regular old x-axis, y-axis, two-dimensional plane. And to this, we're going to add a third axis to get into 3 dimensions. And that third axis is called the z-axis, and it's currently there. It's pointing straight out of the screen at you. GeoGebra has it as a blue dot there, but if I rotate this, you'll see that blue dot is actually our third axis. All right, so that plane that GeoGebra draws for you is your regular old XY plane that you know. And in fact, if I go in and plot a point, let's say I plot the point 3, 2, right? That is the same old 3, 2 that you have always known. I can rotate this here. That point is sitting in the plane. If I rotate this down, that looks like the point 3, 2, right? It's just lying flat on the XY plane. It doesn't have that third dimension. Okay, we'll talk about plotting points in 3 dimensions in just a minute. But this setup, the way that I have it now, with the x-axis kind of pointing towards you and the y-axis almost flat on the screen and z-axis straight up and down, this is usually how we look at the x, y, and z axes in 3 dimensions. And I want to talk a little bit about that setup. So when I showed you in GeoGebra that the z-axis was pointing straight up and then the x and y-axis were usually pointed in a particular direction, this is something that I like to do in the classroom to help students understand that orientation and get them used to something called the right-hand rule. So I'm going to try to recreate this here with some pretty amazing PowerPoint skills and hopefully a corner that's in the room where you're actually sitting right now. Okay, so if we were together in the classroom, I would be standing up here at the chalkboard. Let's see if we can do a little better with that. There we go. There I am standing at the chalkboard. And I would tell you that we're going to put the X, Y, and Z axes in the corner of the room like this. So this is just the positive X, Y, and Z axes. The Z axis, positive Z axis, is going to be the wall seam. So you imagine the negative Z axis would be going down into the floor. The positive X axis and positive y-axis would be these sort of floor seams. And then the negative x and y-axis would be in the room or outside of the room, beyond the corner of the room. All right, so the right-hand rule has to do with your perspective. Okay, so either imagine that you're standing in the corner or actually go stand in the corner. Ah, there you are, you're looking good. So stand in the corner, you're facing out into the room, and I want you to hold out your right hand. Okay, and then I want you to curl your fingertips from the positive x-axis towards the positive y-axis. And that's like in trigonometry, the way that we rotate positive angles, right? We start off at the positive x-axis and rotate towards the positive y-axis. So you've got your right hand out and you're curling your fingers towards the positive, from that positive x-axis to the positive y-axis. And if you do that, you should find that your thumb is pointing in the direction of the positive z-axis. So if you try to do this with your left hand and you try to go from the positive x-axis to the positive y-axis, you will find that you have to point your thumb down in order for that to work. Okay, so we arrange our x, y, and z axes this way, that when you take your right hand, when you curl your fingers from the positive x-axis to the positive y-axis, your thumb points in the direction of the positive z-axis. Okay, so I've posted this picture on our Moodle page. This will kind of help you to remember this. So this is a hand, a right hand that has its fingers curling from the positive x-axis to the positive y-axis. And then of course the thumb is pointing in the positive z-axis direction. All right, and this is almost always how we're going to orient the x, y, and z axes to be able to look at 3 dimensions on a 2-dimensional screen. Okay, so here we're looking at a Geogebra applet. I also have this one posted on Moodle, so you can kind of play around with it, where we're going to talk about plotting points in 3 dimensions. So just like we always list the X and Y coordinates in alphabetical order, X first, then Y, we're going to do the same thing now that we've added the Z axis. So anytime you see an ordered triple, like this 3, 2, 1 down there in pink, it's always going to mean the X direction first, the Y direction second, and the Z direction third. All right, so I'm going to slide this slider down here, and it's going to go 3 tick marks along the floor seam there with the wall. And then it's going to go 2 tick marks in the positive Y direction. So I'm going to go 1, 2. And then from there, it's going to go 1 tick mark in the positive Z direction. So that's going to be up here. And then when we get there, you got the point. And you can kind of rotate this around to kind of imagine there's that 1 tick mark in the Z direction. GeoGebra, you can also kind of slightly spin it. You can spin it a little slower than that if you want to. Okay, so let's just have this applet. Let's reset it. Instead of going 2, let's change that to a -2. And then let's change the Z coordinates to something bigger. We'll say we go to 4. Okay, so now we're still going to go +3 in the X direction, but now it's going to take us -2 in the Y direction. Okay, so again, if you're looking at the corner in your room, so that's going to mean that it's gone outside of your room. Okay, so it's gone beyond that wall that you had where the X seam was. Okay, so it's gone in the negative Y direction, and now it's going to go up 4 until it gets to that point. Okay, so there's everything laying in the XY plane, and we're up 4 tick marks in the Z direction. All right, so I'm going to have it go -1 in the X direction. I'm going to have it go 3 tick marks in the Y direction, and let's go -2 tick marks in the Z direction. And again, you can go play on this applet all you want, just to kind of get an idea of plotting points in 3D. So this time, instead of going out along the floor of the room, it's going to go straight out back on the negative side of the X-axis. So we're going to go -1, then it's going to turn and go +3 in the Y direction, so along this direction, and then -2, that's going to go down in the floor, right? So Z, the positive Z direction is up, so -2 means 2 tick marks down, goes down below, and then rotating this around, you can see that that point is hanging out below the XY plane in the -Z range. All right, so again, I'd encourage you to play along with that applet posted on our Moodle page and get an idea about plotting points in 3D. Okay, so now I'd like to extend the idea of a distance formula into R3. So say we have these 2 points and we want to find the distance between them. This looks a lot like the distance formula for R2, and it should look familiar up until this point before we start adding the z's in there. It's just an extension of that Pythagorean theorem distance formula that we have from R2. So let's just do a quick example using this formula. Let's find the distance between 2 points. Let's find the distance between 315 and 2, -11. Okay. So it doesn't matter, just like in R2, it doesn't matter which one you consider point 1 and which one you consider point 2. Just make sure that you keep consistent. So I'm going to start my square root symbol. It's going to get a lot longer. So I'm going to do x2 minus x1. So that's going to be 2 minus 3 squared. Now subtract the y coordinates, -1 minus 1 squared, and subtract the z coordinates. Okay, so 2 minus 3 is -1 squared plus -2 squared plus, it's a lot of negative stuff, -4 squared. All right, let's see, that gives me 1 plus 4 is 5 plus 16 is 21, so square root 21. All right, so that's the distance, straight line distance in 3 dimensions between those 2 points. So the last thing that I want to talk about in this video is spheres. And we see the equation of a sphere down here, and it should remind you of the equation of a circle. And that should make sense that a sphere is kind of the natural 3-dimensional extension of a 2-dimensional circle. So for example, if I give you an equation like x minus 1 squared plus y minus 3 squared plus z plus 2 squared equals 9. Okay, so we would recognize that as a sphere, and its center is going to read off just like the center of the circle. The center is going to be at 1, 3, -2, and the radius would be equal to 3. All right, so just like with circles in 2 dimensions, with spheres in 3 dimensions, somebody may have come along and taken the formula and sort of foiled everything out, and it makes you lose the information about the center and the radius. Okay, so if we get this, we're going to work it out exactly the same way we did with circles. We're going to complete the square. And we do this the same way we did in 2 dimensions. We just have this third variable now. So I'm going to arrange all the x terms together. So I got a 4x, and then I'm going to leave that blank to complete the square with. Put all my y terms together with its complete the square blank. And then grab that z squared plus 2z with its complete the square blank, and then that 6, I'm going to take and subtract it from both sides, so I get equals -6. Okay, so figure out your 3 magic numbers. If you need to pause it and take a minute to think about how to do that, go ahead and see if you get the right answers. Okay, so for the x's, I'm going to take 4 divided by 2 and square it. That's our magic number formula. So that gives me 2 squared is 4. And then I'm also going to add that over on the right. For the y's, -6 divided by 2 squared, that's -3 squared is 9. I'm going to add that over on the right as well. And then for the z's, I'm going to take 2 divided by 2 and square it. That gives me 1. And just make sure you add to both sides. All right, so I'm going to factor my x terms. That's going to give me x plus 2, x plus 2. And I'm going to factor my y terms. That's going to give me y minus 3 times y minus 3. And then factor my z terms. That's going to give me z plus 1 squared. And then over on the right, let's see, I've got -6. 14 minus 6 is 8. All right, so now we've got the equation of the sphere written in standard form, so I can pick off the center. And that is at -2, 3, -1. And my radius is going to be square root of 8, or 2 roots of 2. So the last thing I'm going to do is hop over to GeoGebra and graph this equation and make sure that it looks like the sphere that we figured it out to be. Okay, so here I have that big equation that we completed the square on typed into GeoGebra, and when I turn it on, it looks like a sphere. Okay, and we figured out that the center was at -2. Let me plot that point. -2, comma 3, comma -1. Right, and if I plot that point, it looks like that point is sitting right there in the middle of that sphere. It's a little hard to tell if the radius is the square root of 8, but we'll just kind of believe that we did that right. All right, I'll see you next time.